Your kind introduction, Mr. Chairman. Today, I'd like to introduce you our developed handheld hair tactile scanner. That is a collaborative research work with Panasonic Corporation and our university. The background, usually we can feel the delicate haptic change in hair daily, but it is very difficult to catch the mechanical sensors because it is very small change and on the surface of hair, very small roughness of cuticle under 0.5 micron. Very difficult for present tactile sensing technology to get. So many previous research work have tried to get the information using optical measurement and hair texture measurement, but in optical method, friction is not obtained, and friction is the most important part of the texture of hair. And also, our previous device is area sensing. That is not micro, so it is very difficult to get the information of cuticle. So we have developed very small area tactile sensor called nanotactile sensor with 0.5 micron radius conductor. This is the tip photograph fabricated by silicon single crystal and using MEMS technology. It has very small conductor area with 0.5 micron tip and small, very small and tiny suspension. Integrating piezo resistor can detect very high sensitivity with, and the surface step resolution is 42 nanometer, and the friction force is below 12 micronewton to get the surface texture of cuticle. And the spatial resolution is below micron. Therefore, we can get the surface texture information by pushing and sweeping, as shown in this slide. And on the surface, a very small cuticle steps we have. But as I said, it is below submicron region. But our sensor device can detect the surface texture information when we sweep from root to tip, as shown in this figure. And what kind? I don't know what happens to. Okay, I will try. Okay, maybe I push the switch. Very sorry for that. Okay, down to the slide. And this is another result when we sweep the sensor from tip to the root. So there are many sharp steps at the cuticle edge. Therefore, we can get higher, larger amplitude of friction force as shown in this figure, and we can detect the submicron cuticle steps on the surface shape information. But this is obtained by a desktop measurement system. That is that we have presented at IEEE MEMS 2012, 22 in Tokyo, and this can only be measured on a tabletop. And strong need, but there is strong need for in situ measurement of hair as it grows. So the motivation of our research work is development of measurement system used anytime, anywhere. This is a conceptual diagram of our hair scanner. Using the hair scanner part, we can firstly push to the hair, then we scan. At the same time, we can get the information of surface texture, including friction force, as I showed. And in this application, it is very important to make stable the measurement situation under the sweep motion. This is the sensor part. So we try to integrate position alignment unit to control the hair position to the sensor tip. This is the essential components of the hair scanner, and totally 3 technologies are integrated. The first one is a horizontal axis hair guide to fix the hair position, and another axis is also necessary to be fixed in vertical axis. And then also we have to get the position information within around a few microns, because cuticle position is very important, and the uniformity is very important to get the health condition of hair. So we use hair scan distance measurement system. First, I will explain about the horizontal guide. Horizontal guide is realized by a pair of glass plates, and a hair is sandwiched by the glass plates and set onto the tip of the nanotactile sensor. The package of the device is fabricated by single nanotactile sensor and two glass plates. Then, apart if the glass plate is not machined, all the part of the hair is contacting with the glass plate, so it is too strong. It is the friction force is too strong, and the hair is damaged. Therefore, we have machined the almost part of the glasses to limit the friction and the contacting area to the hair. Using this configuration, we can fix the position of the hair in horizontal axis. Also, vertical axis position of hair is controlled by two metallic rods, as shown in this figure. The metallic rods works as a guide or limiter of the height of the hair to the contacting tip of the sensor. And the rod position is controlled by screw and springs units, as shown in this figure. And changing the position of the sensor to the hair surface, we can control the contacting force of the sensor tip to the surface of hair. Therefore, the contact force is adjustable and the vertical position of hair is stably kept in this system, even though it is handy. Final part, essential part is scan length measurement system using a rotary encoder. As shown in this slide, hair drives the lever, roller lever, and it drives also the encoder shaft. Therefore, we can get the motion of hair, and we can know where the sensor tip is contacting on the surface of hair. This is the actual device, and the position resolution of the scan measurement, length measurement is 0.5 micron. It is enough to get the cuticle position. And the handy scanner is established by the simple and small core parts of the three technologies. We have evaluated the fabricated hair scanner using this experimental setup, including analog interface and data logger. And this is the essential component engine of the hair scanner. And in this experiment, we use only the engine part. Of course, we can design the outer shell of the hair scanner to be used to measure the hair surface. Of course, it is only the development. And this is demonstration of direct measurement of living hair. She is my secretary, and one her hair is pushed by the hair engine. Please look at the hair cuticle waveform and friction force. First, pushing the hair, then scan from root to tip. We can see here the cuticle waveform at the same time with friction force. When change the direction from tip to root, very much different from the first scanning direction. We can see again push, and from the root to tip, the signal is obtained as shown in this figure. And when changing the direction, the polarity of friction is inverted and the amplitude is very much higher. This is the result, the surface of the hair. When we change the direction of scan, we can get a different texture information. From these difference, we can know how healthy the hair surface or cuticles are. And also we can know the cuticle patterns, uniformity, and numbers. It is important information to analyze the health condition of hair. As we can see, from the root to tip and from tip to root, very much different waveform is obtained from the same measurement system at the same time. So this hair scanner acquires differences in hair cuticle and texture. And these waveforms are almost same to the desktop system as I shown in the first slide. So finally, I'd like to conclude my talk. We have realized novel handy hair scanner system, integrating horizontal hair guide mechanism and vertical hair guide mechanisms. Also, 2-micron position resolution is obtained in the scan distance measurement. Using the developed handy hair scanner, we have demonstrated a handy hair scanner with living hair. So the hair scanner enables accurate data acquisition on hair, and we have successfully detected the hair as it grows. And the signal were as accurate as those acquired by previous desktop system. So we have concluded the small size hair scanner has taken off from the desktop. Okay, these are the acknowledgements. Thank you very much for your kind attention.